Okay, in this video we're going to take a little bit of a detour from talking about electronics and electrical components and so on, and we're going to talk a little bit about how streams of particles can deflect inside of magnetic or electric fields. So we've been talking about interactions between magnetic fields and electric current and how magnetic fields can produce electric current and so on and so forth. It turns out that flowing particles or streams of particles such as nuclear radiation, which is what we're going to talk about in this video. We'll ignore this part of the diagram because we don't talk about positrons in this course. But yeah, we'll just look at these three: alpha particles, gamma rays, and beta particles. So we're going to see what happens because a stream of particles counts as electric current. So if there is electric current, because of course current is moving electrical charges, these are electrical charges and they are moving. So if they go through an electric field or a magnetic field, then they are going to experience some kind of a force. So we want to talk about that, just kind of lay it out pretty quickly, and then we'll move on back to talking about electricity and so on after this. All right, so we're going to need our left-hand rule again in order to figure out what's going on here. Let's start with the easy ones. If you have neutrons as radiation or gamma rays, those are both uncharged. So I'll just leave neutrons there because we can talk about that if we want. Neutrons are released by fusion or fission. So those can be released, especially in nuclear power plants. You get neutrons as nuclear radiation. But anyway, so neutrons or gamma rays, they're uncharged. So since they have no charge, they have no current, and they're just going to go straight through a magnetic field without any deflection. They just fly straight through as if it weren't there, right? So let's look at alpha particles first, as far as a charged particle moving through a magnetic field. And if you do your left-hand rule, right here, I have it basically set up in the right direction for an alpha particle. Your first finger should point in the direction of the magnetic field. The magnetic field is shown as these green circles, and it's going straight into your screen. So the direction of the magnetic field is basically coming from you into your screen. So you would point your finger straight at your screen, first finger of your left hand. Current is the direction of the positive charges flowing, and since alpha particles are positive, then they're flowing out this way, right? So that second finger should point this way on your screen, which is what, to the right? Right. So your second finger is pointed to the right, your first finger is pointed into the screen, and that should leave your thumb pointed upwards. So then you see the stream deflects upwards. It doesn't go straight up. It's not like, there's no right angles here, okay? It just curves in an upward direction as shown on the diagram, all right? If we were talking about positrons, it shows the positron bending more, and the reason for that is that an alpha particle is much more massive. Since it's much more massive, it has a lot more inertia, and it's harder to make it bend. So it's going to maintain its momentum better and maintain its trajectory more, so it's going to bend less because it has more mass. The positron would bend more. Even though they both have a +1 charge, this one is the same mass as an electron, so it would bend a lot more in the same magnetic field than the alpha particle. All right. Now here's where it gets just slightly tricky. A beta particle is a minus charge. So the field is still straight into the screen, so first finger points into the screen. Got that? But remember, your second finger has to point in the direction of conventional current. Right? Conventional current, which means flow of positive charges. But a beta particle is negative. So that means that you have to point your finger backwards. All right, so the beta particle is traveling to the right, but if there were positive charges flowing, they would be going to the left. It's really weird, I realize that, but basically when you're talking about moving minus charges, you have to pretend that current is going the opposite direction of the motion of the minus charge. So the result is your thumb points downwards. So first finger should be pointing into the screen, second finger should be pointing to the left, and then that leaves your thumb pointing downwards, which is the direction that the beta particle will deflect in this magnetic field. Of course, if you make the magnetic field stronger, there will be a greater deflection. If you make the particle slower, it will deflect more. If you make the particle faster, it will deflect less. And again, a beta particle is much less massive than an alpha particle, so it should bend more than the alpha particle in a magnetic field. So that's basically deflection of nuclear radiation in a magnetic field. Let's look really quick at the deflection in an electric field. And this one is much more straightforward than the previous one. Just recall that a beta particle has a minus charge, an alpha particle has a plus charge, and a gamma ray is neutral. So again, if you have two electric plates, one of them is charged positive and one of them is charged negative, then your gamma ray is just going to pass straight through without any change. Your beta particle is going to be attracted to the plus, so it will bend in this direction, and your alpha particle is going to be attracted to the minus, so it will bend in this direction. Now I've drawn them the same, with the same amount of deflection, just because I haven't been able to nail down for sure which direction these bend. So we're going to go with whatever your book says. But I have seen basically information that suggests that a beta particle deflects more and other information that suggests an alpha particle deflects more in an electric field. So without doing the experiment myself, I'm not totally sure. We'll just go with whatever your book says, and otherwise just understand that the beta will be attracted to the plus and the alpha will be attracted to the minus, and that's the direction that they'll bend. And that's it for an electric field. That's pretty simple compared to the magnetic field. All right? So that is what you need to know about deflecting particles in fields, electric fields or magnetic fields. Interestingly, as a side note, in this particular setup, if you happen to know the speed of, say, your alpha particle, how fast it's moving, and you know the voltage that you're applying across these plates, and then you measure how much it deflects, you can use some equations to figure out the mass of that. Or same thing with the beta particle. If you know the speed that it's traveling, and you know the voltage across these plates, and then you see how much it bends, you can calculate the mass of that particle. And in fact, that is the exact method that J.J. Thomson used in order to determine the mass of the beta particle, or of some electrons that were flying through a thing like this. And he determined that the electrons were way, way smaller than anything they had ever known, and that's how he found the first subatomic particle, was using a setup similar to this. So that's pretty cool. Little side note. Anyway, that's it for this video. Thank you for watching, and hope it was helpful, and we'll catch you next time.